read the value of x. Hold it up. Hold up the value of x. What is the value? No, don't look at the screen. That's the value of x over there, right? There's 2, right? Hi, Neil. There's 2, right? And then what are you going to do? You're going to add 1 to it. So, no, you're going to add 1. Don't say maybe, dude. You have to execute the code that I wrote. You don't get to execute your own weird code, right? I am the programmer. You are the computer. Just go with it. But before he gets to, right, he adds 1 to it. Excellent. Before he gets to it, what's your name? You're Peter as well? Okay, close enough. You, the second thread, comes through here, and they execute the same sequence of code, right? Read x. What is currently the value of x? Hold it up. This is the audience participation part of the talk. Now, you add 1. Now store it back, which means you get what he has. And now we switch back to you and you store it back. What happened? I mean, this is classic canonical threaded concerns, right? And in an abstract mathematical sense, yeah, okay, this is bad. But if we're talking about your bank account, or if we're talking about your credit card account, or if we're talking about US banks, right? This is clearly a problem. And this is the basic reason why we want to start thinking about programming in a more mathematical sense. You guys can sit down. Thank you. If we start looking at the principles of mathematics from way back when we were in school, remember when you used to solve equations? Remember when you used to do stuff like this? Right? Or maybe not. Maybe you don't remember. Maybe you had way too much vodka last night. I don't know. Anyway, when you did stuff like this, typically the way you solved these particular pair of equations is you figured out some value for x, right? X equals 5 minus y. And then thanks to the notion of substitution, you could take that x equals 5 minus y. Equality implies that I can do replacement. I can take 5 minus y and drop it anywhere that x shows up. And so I drop it into the second place, and so 5 minus y equals 1. Oh, okay, now I can solve this in terms of the one remaining variable, blah, 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 right? I can start figuring out some of these things. I can start doing that kind of substitution. The programmers of the world look at this and say, you know, if I can do that kind of substitution, it means that I don't have a couple of things which are bad. I don't have shared state. I don't have mutable values. And those two things are what we are trying to protect against precisely when we start talking about concurrent code. Now, why is everybody so bent out of shape over concurrency today? I mean, you know, come on, right? The engineers at Intel are masters. They are wizards. They are able to figure out how to put more and more and more transistors on a given chip. You guys know about Moore's Law? Have you heard this? Gordon Moore from Intel, right? The guy who said basically that we can get the number of transistors on a chip to double roughly every 18 months. Now, historically, that has meant that processor speeds have doubled every 18 months. Now, a couple of years ago, actually more like 4.5, 5 years ago, I bought this ThinkPad, right? It's a 2 gigahertz ThinkPad. And let's see, that was 2004, 2005, somewhere in that time frame. So according to Moore's Law, let's call it 4.5 years because that makes 3 Mooresian cycles, right? So let's see, 2 gigahertz doubled makes 4 gigahertz, doubled makes 8 gigahertz, doubled makes 16 gigahertz. How much does a 16 gigahertz processor cost in Poland anyway? Because I need to buy a new laptop. You're all laughing, why? Do you not have 16 gigahertz processors? None of us do, right? Why? Because Intel ran into a limitation that not even the wizards, the amazing, wonderful engineers at Intel could get around. You know what that limitation was? The speed of light. Intel discovered that they could not get, because of all the transistors on the chips that they were trying to build, they could not get signal to travel from one end of the chip to the other in a single clock cycle. And a lot of their chip design is predicated on that basic idea. And so Intel said, you know, since we can't figure out a way to make light go faster, I mean, they can do lots of things, but they have not yet figured out how to make light go faster. So what they said is, let's do this. Instead of trying to get light to go faster across the chip, let's carve the chip in half. And we'll call it a core duo. And we'll do this again, and we'll call it a quad core. And we'll do this again, and we'll call it an octo-core, and the next one will be a deca-sexa-core, and the next one will be a never mind. I don't even want to know what it's going to be when it's 32 processors. Because that's the world that we're walking into. Not where processors are going to get faster, but where we're going to need ways in which to make our code execute in parallel more efficiently. Not just efficiently from the machine's perspective, but efficiently from our programming perspective. Because think about this for just a second. If you're trying to take full advantage of a 32-core processor, try doing that in C# today. You spin up your own threads, or you make use of asynchronous delegates, right? You're going to create a delegate instance, and then you're going to invoke it with begin invoke, and then you're going to have to harvest the results with end invoke. And by the way, even if there are no results to harvest, you have to call end invoke, otherwise you'll leak resources until the process dies. How many of you like this model of programming? Come on, be proud. Hands in the air. Got one guy who's thinking, wait, if I can figure this stuff out, I will never be fired again. The rest of us are going, wow, I really hope that I can go off and get a new job before this code goes into production. Because that's what a lot of people's mentality was. This multi-threaded stuff kind of scares me, and so, you know, I'll work on it for 12 months, and then right before the release, I'm going to go to the most important website every programmer needs to know, www.dice.com, and I'm going to find myself a new job, and you know what? If it fails, I'm not the one who has to fix it. Woo-hoo. Let's go. Does this make a little bit of sense? Sort of set certain amount of context, shall we say? Okay. How many people wish I would shut up and just show you code? Go ahead, Neil. Raise your hand. I know you want to. Yeah. There we go. Oh yeah. Now that Neil does, these guys down here suddenly feel bold. Oh well, you know, I know him. He's a friend. He comes over to my house and drinks my scotch. You people do not, so I can beat up on you. All right. So let's do this. We'll come back here to Visual Studio. Okay, a couple of things. First of all, yes, this is Visual Studio. Next question. Is there anyone who's not familiar with this product? If so, you probably want the Java session down the hallway. All right. So again, created this by using the F# tutorial project. I don't know that the production bits, the stuff that will ship in February, I don't know if they will include that or not. Again, all that's here really is just sample code. All right, there's nothing magical about the tutorial other than the fact that there's just sample code there. As you can see, the / is a comment in F#. Any questions? This syntax here, the #light syntax, we use this because F# actually has a history predating Visual Studio. As it turns out, F# was actually the creation of a gentleman by the name of Don Syme at Microsoft Research. He's been interested in functional languages for a very long time. And so he, many years ago, back when .NET was first being released, he decided he wanted to create a functional language on top of the .NET platform. Now, in order to do that, as we'll see in a little bit, he needed some more support from the platform. So he actually went and created some additional enhancements to the CLR itself, which was released as a source patch to Microsoft Rotor. Those of you who've not heard of Rotor before, this is actually Microsoft's source available version of the CLR. I say source available as opposed to open source, because open source has some legal implications there that are not the case for Rotor. So you can't submit patches or any of that kinds of stuff. But if you want to know how the CLR works internally, how do classes get loaded, what do they look like in memory, etc., you can download the Rotor bits and build them yourself, and it'll run on top of Windows or BSD. A couple other platforms, people have submitted source patches, etc., etc. He released this patch,
and then used that as the basis by which to build this language. Do you know what that patch that he introduced was, by the way?